Welcome back everybody to our last talk. Thank you for joining still. So the last talk will be by Jinwoo Sung from the University of Chicago and I guess moving to the University of Washington about the random walk reflected of infinity. Thank you.
All right, thank you. And thank you for the organizers for giving me a chance to talk. I'll be talking about work with my PhD co-advisor, Ewain Gwynne. And indeed, I am moving to Washington, which is not in the East Coast, but it's in Seattle. It's Washington State in the fall for postdoc. Okay, so this is what the main object is. We want to do a random walk on the. So think of the. You can maybe think of the dual graph of the circle packing. We want to do a simple random walk on this graph. So at each point, you choose equally between each of its neighbors to take the next step. If the graph is transient, then you might go all the way to infinite end. But the idea is that maybe if it has some conformal structure, then we would want to do something like a reflected Brownian motion. So reflect the random walk off of its infinite end and continue the random walk. So for the first part of the talk, I will discuss the construction. It's going to be quite elementary. And in the second part, I will try to connect it with Ewan's talk on supercritical LQG on Tuesday and other themes that are more relevant to the workshop. Okay, so this picture was not from me. It was this simulation of a CP hyperbolic triangulation of over an angel. But the setup is that let's look at infinite graphs which are locally finite connected, and for which the random walk is transient. And really, you should think of maybe these two examples in mind, that they could have infinitely many ends, as opposed to, say, a random walk on an integer lattice in d dimensions. So for this one, each of these points on the boundary is an infinite end. For this picture, this is a simulation of a random planar map in the universality class of supercritical local quantum gravity by J. Park. Here, the infinite ends are inside the domain, so we want to have a random walk that reflect off of these infinite ends, which could be uncountable.
Ends are edges here, or?
Sorry?
Ends are edges here, or points that touch the circle?
So sorry. This one is we're doing the dual graph, random walk on the dual graph.
Okay.
Yeah. Okay. So one of the main tool is going to be to look at the harmonic functions, because harmonic functions encode random walks and vice versa. So we can think of random walks with. So for the rest of the talk, we'll be dealing with simple random walks for which we have equal probability of moving to different neighbors. We could do the same argument on graphs with different conductances, but for the sake of simplicity, we'll stick to simple random walk, and here the harmonic function on the graph is the one that whose value at each vertex is equal to the average at each of its neighbors. So if we have a finite graph, we can, it's one of the elementary facts that we can have a solution to the Dirichlet problem using random walks. So if you have a finite graph and a finite subset of the graph and a real valued function given on it, then we can extend to a harmonic function of outside of this finite subset by simply looking at the expected value of the function phi when the random walk hits the set A. So going forward, this tau A will always refer to the first hitting time of the random walk at whatever that is the subscript. Okay, but if the graph is infinite, there could be multiple harmonic extensions. So to take a simple example, if we look at the zero function on this finite set, then it could be extended to the zero function everywhere on the graph. Or if we have a transient random walk, then we can just look at the probability that the random walk doesn't hit the set A. Right. So for an infinite graph, there's the ambiguity on what is the correct harmonic function that represents the movements of the random walk reflected off of infinity. But the idea is that actually, if we look at the energy minimizing harmonic functions, this is going to give us a unique harmonic extension that is related to the random walk that we want. So again, the Dirichlet energy is given as the sum of the squares of the difference of the value of the function at two neighboring vertices. Another way to think of it is the L2 norm of the flow, which is given by the gradient along each edge. Okay, and this is the main tool that we use in our construction. We couldn't find it anywhere, so we proved it ourselves, but the proof is quite elementary. The idea is that if we have a finite set and a given function on it, then we have a unique harmonic extension that agrees with the value of the function phi on the set A and is energy minimizing. And one nice property is that this harmonic extension is linear in the function that we are given if we have the fixed set A, which will turn out to be useful. Okay, so let me give you the proof right away. So again, the idea is to notice that the energy, instead of the function on the vertices, we look at the flows on edges. So this E with arrow refers to a set of directed edges. So the Dirichlet energy, again, is the L2 norm of the L2 norm of the gradient of the function on the vertices. And let's look at the subset, which consists of gradient flows for which the function will be 0 on the given set A. Okay, and it's easy to check that this is a closed subset of subspace of data. So this is going to be the flows corresponding to those without cycles and zero potential on the set A. Okay, and then what we should do is to just look at some finite energy extension of the given function. So here, given the assumption, we can just extend it by a zero function, and since the set A is finite and the graph is locally finite, this will give us a finite energy extension. And let's look at the projection of this finite energy extension, the gradient of this finite energy extension to this set A. Okay, so we actually okay, so in fact, if we look at if we subtract this, okay, so given this projection, since the graph is connected, we can follow along the path so that we obtain the function whose gradient corresponds to the projection, such that the boundary value, the value of the function is equal to A, 0 on A. Okay, and the idea is that if you look at this function here, okay, so it's written in a bit of a way, but because of the properties of the projection, the linearity is immediate, and because this function is has the boundary value A, it's going to be phi on the boundary. Okay, and the energy, if you think of any other function which has the boundary value phi with finite energy, then the the notation should be that this is just not the gradient, but just the phi minus f. The energy of the phi, any other function with the boundary value phi should be given by phi hat minus f of some form. So by the property of the gradient, the energy will be minimized uniquely at this projection. Okay, and so finally, this has to be harmonic, because otherwise, if it's not harmonic, we can replace it with the average at a specific vertex where it's not harmonic, so that the energy is strictly decreasing. Okay, so elementary proof of the proposition. Okay, and With this, we can define the energy minimizing harmonic measure that the random walk reflector of infinity should satisfy. So let's just define it with this notation. So what this is it's the hitting probability of random walks started at x reflected off of infinity. When it hits a, it would end up at y. Okay, and let's define it as the harmonic extension of the indicator random variable at this point y. Okay, and then the linearity comes in handy because then all the indicators sum up to 1 on the entire set phi, so it's going to be a probability measure. Okay, and the idea is that for the random walk reflected off infinity, if you restrict to excursions within the set A, then once the random walk reflected off infinity goes away and starts from a different vertex outside of the set A, this should be the hitting probability from which we can continue the random walk. And so we're going to try to define the random walk reflected off of infinity by looking at excursions on finite subgraphs of the graph. So let's take a sequence of finite connected subgraphs, which increases the graph G. Let's define this y sub kn as a notation for what it should be the excursions that stay within the graph, the subgraph G sub n. So the transient probability is that inside of the graph, so if this blue part is the finite subgraph inside, if the vertex is just inside and there are no neighbors that are outside of the graph, then it just does the usual transition probability of choosing equally from its neighbors. When it goes to the boundary, it has a choice of either jumping to the nearest neighbor, which is inside the graph, or at a distance of 1 away from the graph. So this part represents if the random walk stays within the Gn, this is the part that contributes to if these jumps. If the random walk leaves the domain, then from here, so this vertex is chosen with probability 1/degree of x, and then the probability of returning to this vertex here is given by these energy minimizing harmonic measure. So this is just this is the transient probability starting from here that we end up at this vertex. Okay, and with this random walk, so we have a sequence of different, for each finite subgraph, we have a random walk. And this is just to say that these random walks are consistent if you first look at, so here n is, let's say n is greater than m, so this is random walk restricted to excursions in the larger subgraph, and then we further restrict that to smaller subgraph. Okay, and then this lemma just said it's consistent. The way to check this is that both you run the random walk on the larger subgraph, and you look at the hitting measure on the smaller subgraph, and this is just you take the smaller subgraph and you look at the harmonic minimizing energy minimizing harmonic measure, and they both satisfy the same transition rule. So this one is trivial because this is just random walk, the transition probability for the random walk on the larger subgraph. For this one, the thing to notice is that if you first know the value of these energy minimizing harmonic functions, harmonic measures, outside of the, sorry, I think maybe x and y are switched here. I'm sorry for that. If you know the harmonic function on the larger subgraph, then the energy minimizing extension of that is given. This agrees with the energy minimizing harmonic extension outside of the larger subgraph when you already know the value of the extension to a larger subgraph. Okay, and by the maximum principle, they agree on the outside of in the larger subgraph. So this, looking at this transition probability, all that you need to check is that once you leave the smaller subgraph, is the transition probability going to be the same when you restrict to excursions in the smaller subgraph? So this is enough to show that the laws are consistent. Okay, and so with that we can couple these different random walks so that the restrictions of random walks on the larger subgraph restricted to smaller subgraph is the random walk on the smaller subgraph, and we just take the projective limit. Okay, to put it concretely, we define a random equivalence relationship where these are considered equal if n is larger than m, if we take the random walk on the larger set, and if we restrict it to the smaller subgraph, the jth point in this random walk is given by kth point in the larger random walk before restricting. So it's just this equivalence relation gives a random totally ordered set that gives us that tracks the time for our random walk reflected off infinity in the projective limit. Okay. Is all this okay? Okay, and we can also get a continuous time version of this random walk if you don't like the random index set. So for this, of course, we need to speed up the random walk for infinite points far away from the point that you started with to put everything into a real line. And to do this, the point is that it is possible to give a weight to each vertex, so that we have a continuous time Markov chain with a jump rate given by this vertex weight, such that the hitting probabilities are identical with what we had in the previous slide.
Why do you need to speed up?
Well, if we just move, originally, right, the random walk, if you just spend unit time for each of these jumps, then we would already spend all our infinite time going to the infinite end, but we want to continue gluing these things.
Okay.
And these excursions away from infinity, right, it could be that we would actually have to make an infinite amount of excursions in between going inside and going out to see a point where we are macroscopically away from the boundary again.
Okay.
How did that show up in the discrete setting?
The discrete setting,
yeah.
for this with this random time index.
Yeah. Okay.
So what it is that, right, so each of these excursions away from infinity would be a copy of Z. Mm-hmm. So this is some linear ordered copy of where you glue complementing copies of Z. Okay, so that was the construction of the random walk reflected off of infinity. You can now ask, can we use this for anything? Can we somehow see that this is related to other statistical physics objects that we consider? So one example that we found is that of the uniform spanning forest. So on a finite graph, a uniform spanning tree, it just means you sample from a tree that spans all the vertices from its uniform measure. And as so here Gn is again the set of finite connected subgraphs which increase to G. So you look at the projective limit of all in these uniform spanning forests. So what this means precisely is that if you have any finite subset of the edge set, then the distribution of the intersection of the uniform spanning tree with this edge set converges to the intersection of the projective limit with the edge set. So the projective limit will again will not have any cycle, but it could be that it is not connected, and hence the name, the forest. So this is called the free uniform spanning forest. There's also the wire uniform spanning forest version, where instead of you looking at uniform spanning forest on the subgraph, you add another point. You wire all so here you wire all these points which are immediately outside of your finite subgraph to a single point, and then sample a uniform spanning tree on there, and then you again take the projective limit. And in this, so the definitive source for uniform spanning trees is this book of Lyons and Paris, Probability on Trees and Networks. So this picture was taken from that book. So as you can see, uniform spanning forest can, so this, the free uniform spanning forest here is all connected, whereas the dual is has infinitely many components. Okay, but in the connection with the random walk reflected off of infinity is that random walk reflected off of infinity gives a way of sampling this free uniform spanning forest in a algorithmic way. So that is so there's the Hausdorff Broder algorithm in the finite vertex case already gives a uniform spanning tree. And if you take the random walk reflected off of infinity version of it, then this gives a free uniform spanning forest. To describe the Hausdorff Broder algorithm, what we do is we just look at the random walk. We run the random walk until the first time it hits a new vertex, and then we add the edge corresponding to the jump to the vertex that we visit for the first time. So to put it concretely, for each vertex that we are not starting from, there exists a unique ancestor, and then we put in the edge corresponding to this ancestor and the jump, the edge that corresponds to the jump into the vertex X. And this gives a spanning graph without a cycle. This is the Hausdorff Broder spanning forest, and you and I were able to prove that this has the same law as the uniform spanning forest. I'll mention here that the wire spanning uniform spanning forest case was already considered by Tom Hodgcroft, not using the random walk reflected off of infinity, but by random interlacements. So random interlacements, if you are aware of it, is a similar kind of process where instead of reflecting off locally, all the infinite ends are wired together. So your excursions could jump to a different end and continue there. So this highlights the fact that our random walk reflected off infinity is has a free boundary condition, whereas the random interlacements corresponds to the wired boundary condition. Okay, but the algorithm that is another algorithm that is used to generate the uniform spanning tree that is more powerful often than the Hausdorff Broder algorithm is the Wilson's algorithm. So we can ask, can we use the Wilson's algorithm using this random walk reflected off of infinity and somehow also get a uniform spanning forest? So to really clear, so what is this? So Wilson's algorithm consists of putting edges which come from loop erasures of random walks. So how do you define the loop erasure of random walk that hits off infinity? So our idea is to just try to do the same thing. It could be that if you start from a vertex z and you try to go to the vertex x up to the first time, if you look at the path from z to x, it could be that the entire path is finite, but maybe the path is going to be infinite. Okay, so what it is, I mean, probably know, you take the random walk, and when you visit a vertex you have visited before, then you remove this entire loop, and you continue doing random walk. So you remove this loop again, maybe this loop removes this entire loop, and then you continue until the first time you visit x. So this path is going to visit each vertex once, and so that's the chronological loop erasure of the random walk there. And it could be that, right, indeed, the path could take infinite amount of time, hitting infinite ends to reach the point x. But it could be that all the loops that are created by this path contain all of the infinite excursions to infinite ends, in which case the loop erasure will be a finite path. Or it could be that then it's well defined, or it could be that the loop erasure, if you do it chronologically, might go off to an infinite end. And then you just say this path all the way to infinity is a loop erasure. The reason for this is that the loop erasure is defined using iteration, so it really is an induction that builds it off. So to erase the loops after it touches the infinity, the loop erasure touches the infinity, you somehow need to have a way of erasing loops from time minus infinity, which is not obvious how it should be done. Okay, but we could try to, the Wilson's algorithm builds a spanning graph without cycle using this algorithm. So what you do is you enumerate the vertices in some arbitrary way. You start from a singleton, and then each time you start a random walk. So for k equals to 1, you start a random walk from x1 up to the first time it hits x0, and you add in the loop erasure corresponding to this random walk. And for k equals 2, you start from k to x2, you start a random walk until the first time, this time not hitting x0, but rather the tree that we get after the first, or the graph that we get after the first recursion, so x0 and the path. Okay, and so if you do this for all k, we will have be included all the vertices, and this is a graph that consists of this is a spanning graph without a cycle. However, the two laws are not exactly the same. They are the same if we restrict to the event that the tree that we get, the forest that we get is connected. So if you restrict to the event, we restrict to the case that this the forest is connected. So if it's a tree, if you restrict to the case that the free uniform spanning forest is connected, then the two random graphs agree in law. And the reason is that it could be that the Wilson's algorithm could block off certain section from going all the way to infinity, which one? Sorry?
Is there a formula for the probability of that event?
We can get it using the similar way as a transfer matrix. Sorry, not the transfer matrix. This matrix representation that Pimentel has. Yeah.
Thank you.
Yeah. However, if it is not clear when the graph is going to be connected or not, and in fact it is an open question whether the number of components of the free uniform spanning forest is almost really constant or not. For the wired case, this was proved by Liouville and Schramm using Wilson's algorithm, but there was not a problem because there's only one infinity, so they could root the uniform spanning tree at infinity. And once the random walk hits infinity, then that's just the end. Okay, now let me connect to what Ewain talked about on Tuesday on the supercritical oval quantum gravity, which was the motivation for why we started this project. So to recap, let me just recap this talk quickly. The idea is that instead of this coupling constant gamma, which appears in the Gaussian multiple chaos e to the gamma times the Gaussian free field, we should look at the different parameters, either the central charge or the background charge, because so this is the difference between the supercritical Gaussian multiple chaos and the supercritical version of local quantum gravity. Is that for supercritical Gaussian multiple chaos, you might want to increase gamma greater than 2, or look at complex values of gamma, but instead the idea is to look at the central charge that is less than the subcritical regime, which is between 1 and 25, and the corresponding background charge Q, which is given by this formula. It takes a real value in this regime as well. It's between 0 and 2, and the idea is that as this factor decreases, then this the surface becomes more and more singular. And this background charge Q appears as the when you look at the conformal coordinate change rule for the field. Okay, and again, the idea was that that Ewain had was to mix between this critical quantum disk with central charge equal to 25 or gamma equals to 2 with an independent zero boundary Gaussian free field. And in particular, how much you rotate the two fields is determined by this parameter Q. And in Ewain's paper with Moore and Sung, they had a coupling between Gaussian free, the supercritical LQG disk and the CLE4, where the CLE4 came from this field corresponding to zero boundary GFF. So, and there was an analogous result that they proved that if you look at an independent CLE4, which is independent because this comes from the zero boundary Gaussian free field, it's independent from the quantum disk field. Each of the surfaces inside have the same law once you map it out modulo, if you know all the boundary lengths of the curves. Okay, and from this, they suggest a discrete model for a supercritical low quantum gravity disk. So try to juxtapose the two pictures. Then what you get here, this corresponds to the gasket of the CLE4. And inside we want to put in these surfaces which are supercritical LQG disks. And these are surrounded by these rings which are dual to the CLE4 loops. And the peculiarity of the supercritical case was that the inner and outer boundary, we had to put in rings that actually change the length of the inner boundary length and outer boundary length between the between the two sides of the loop. And this distribution was determined specifically in terms of the WQ, and really the reason that this comes in is because the supercritical LQG boundary length is determined simply as the critical LQG boundary lengths, which can be done because the zero boundary GFF is constant along the boundary, but because there is a height gap in the coupling between the level line coupling of Gaussian free field and the CLE, there's going to be this gap contributing to the change in the boundary lengths inside and outside of the CLE. So that's why for this discrete model of supercritical LQG, we add in rings that change the boundary lengths, and getting the looking at the analog of the gasket decomposition for the subcritical or Venn model, what we do is we iteratively put in more and more loops inside, which corresponds to nesting of CLE4. So because of this tilting of the boundary length, it could be that this recursive iterative procedure could be terminated after finally many steps, or it could actually go on for infinitely many steps. And so in particular, if we define this n as the Pn as the law of this the object that we get, where initially we started with also a map of boundary length n, then as n tends to infinity, wrote in a paper with Van Ambatia and Ewain last year that this probability that this procedure terminates in finite time is going to be exponentially rare, and on this condition, on this event, it's going to converge to continuum random tree. So there's no interesting geometry. And the main idea is that to obtain an interesting two-dimensional geometry in the supercritical regime, then we need to actually consider discrete models which have infinite volume a priori. Okay, but then this raises a question: how do we actually connect the discrete model, which has an infinite volume, with the continuum model and the Gaussian free field there? So that's where the random walk reflected off of infinity came in. And the idea is that for the subcritical models, you first fix the complex structure coming from the discrete model, and so that the discrete complex structure converge to the continuum complex structure, and then you can just look at how the metric is changed, because then the conformal change of the metric is given by the exponential of the Gaussian free field. So the idea is to first find an embedding of the discrete map into the plane, which comes with a correct conformal structure, and then you can look at what the limit should be. So the first step for our this map, this random planar map with infinite volume would be to first put it into a disk with the correct conformal structure. And there are many ways to do this, and many wonderful results, which proved the convergence of discrete planar maps into the continuum limit with different embeddings. One example is the circle packing that was in the first title page, where it comes with a conformal structure. Another way could be the card embedding, which is based on the crossing probabilities for percolation clusters. But the one that we use is the Tutte embedding, which uses the conformal structure coming from the random walks. Okay, so the Tutte embedding, let me give you the definition. Okay, maybe it's better for me to just draw. So idea is that you first fix one vertex in the bulk and another vertex in the boundary, and send each of them to 0 and 1. So these are x0 and y0. And then you embed the boundaries on the vertices on the boundary. So you start adding each vertex so that the arc length here corresponds to the harmonic measure of the random walk hitting this point for the first time. So this length here would correspond to the rate. This length divided by the total circumference corresponds to the harmonic measure of the random walk started from here hitting this point. So that's all the embedding of the boundary vertices, and then you put in the interior vertices. So that the interior vertices are put in, so that if you start the random walk from here and look at the harmonic measure from this vertex, this agrees with what would be the case for Brownian motion on the disk. So in particular, for this random walk reflected off of this graph with infinitely many vertices, we can look at this function psi, which gives you the locations, complex locations of all the vertices on the boundary of the unit disk, and then take the energy minimizing harmonic extension of this function to the inside to the bulk vertices. So the upshot is that the harmonic measures for the random walk reflected off of infinity on this graph agrees with that of the Brownian motion on the disk, where you identify each of the boundary vertices with the arc preceding it. Okay, and so this embeds all the vertices, and the edges are simply the line segments connecting the two vertices, and you can also check that the bases are going to be convex regions. So this is a simulation by Jason Miller of this mated CRT map, which corresponds to some discretization of the Liouville quantum gravity surface in the subcritical case. And Ewain with Jason Miller and Scott Sheffield showed that the Tutte embedding converged to subcritical Liouville quantum gravity. And the idea is that this should be the case, should be the true for infinite vertices as well. One fact is that this is also what we would want when we try to do Tutte embedding of a graph with infinitely many vertices, because if we have a finite subgraph, again, approximating the infinite graph, then the Tutte embedding of the finite subgraphs do converge to the Tutte embedding of the infinite graph. However, at this point, it's one of the basic questions that could be asked, which is not obvious from the construction, is what are the images of the infinite ends of M? So in the beginning, the two examples were that maybe in the case of the hyperbolic triangulation, the infinite ends were, after the embedding, a connected set, whereas here, this infinite ends should correspond to a totally disconnected set, which, based on the work of Leonie with Ellen and Ioannaru, because the singular points somehow are connected to the points surrounded by infinitely many CLA for loops. Okay, but with this definition, so what we obtain at the end is we can state a conjecture for what the convergence of discrete model with infinite volume that corresponds to supercritical LPG should be. So we would expect that this Tutte embedding, given in terms of so this is a discrete map, and the boundary has finitely many vertices, but in the interior we could have infinitely many vertices. So after the Tutte embedding, well, the counting measure on the boundary should be the length measure on the boundary. The graph distance should be the supercritical LPG metric. The loops to CLE4, Brownian motion, random walk to Brownian motion, these things should naturally hold. One thing that is outside of that's left out is that we don't consider the counting measure on the bulk vertices because we were able to see in an earlier work that there is no volume measure in this particular case. I mean, there could be a volume form, as Roland pointed out, but at this point, I mean, it should not be simply the limit of counting measure on the bulk vertices. So we don't have a formulation for that conjecture. So, okay. Would there be any question at this point? Okay. So let me end by some more conjectures on what are interesting phase transition behaviors that we can conjecture if we put in the models that were considered in other talks during this week to supercritical L2G disk. And the main idea here is that for Q between 0 and 2, the supercritical LPG metric was constructed by Ewain and Gwynne earlier. And what they observed is that there are singular points of the metric which are at infinite distances away from every other point. And these are intimately related to the thick points of the Gaussian free field. So here, HR of Z is, as usual, the circle average of the field at point centered Z at radius R. And this is the usual definition of the thick point. Pfeffer showed that almost surely all points of thickness greater than Q are singular with respect to the supercritical LPG metric with parameter Q. And if the points are of thickness less than Q, they're not singular. Okay? So the main idea for these conjectures that are forthcoming in the next few slides is that if you look at some sort of a model that is independent from the supercritical LQG, if you see the intersect, if you want to find out if this model or the set, some certain set, intersects with the singular points which are of thickness greater than equal to Q, then it suffices to check the Hausdorff dimension of the model that you were looking at, thanks to the KPZ formula. So in particular, here we just need to check if the Hausdorff dimension is less than Q squared over 2, then almost surely it will not intersect the singular points. So considering the model that we had, the free uniform spanning forest. Okay, so by the Alder's broader algorithm, the branches of free uniform spanning forest are loop ratio random walks. And so these free spanning force is connected if these loop radius random walks are not going to infinity. Okay, and just considering locally these random walk, this loop erasure should converge to SLE2, and SLE2 has Hausdorff dimension 5/4. So if the central charge is greater than 16, then it does not hit the singular points and should be connected. If it's less than 16, then it should hit many components. So again, as the central charge decreases, the surface is becoming more and more singular. So that's why the inequalities are in these directions. Okay, one more model that we can talk about is the percolation on these discrete models of supercritical QG. So we would expect that there would be a critical probability for the percolation on this map. And at criticality, at this critical P, which could depend on the central charge, probably it does, it should be a CLE6 gasket. So CLE6 gasket, as Hausdorff dimension 91/48. So this corresponds to central charge greater than 95/4, which is slightly less than 25, which is the phase where the supercritical phase starts. If this is the case, then the CLE6 gasket does not intersect the singular points. So there should be infinite. There should not be an infinite open cluster for smaller central charge. The surface is most singular, and there should be an infinite open cluster on the discrete models of supercritical QG if you run critical percolation on these models. Okay, so I guess it's the last talk, so let me end slightly early, and thank you for listening.